Good morning to everyone on the West Coast, good afternoon to everyone on the East Coast, and good evening to everyone joining us from Europe. Welcome to the NEO Technology Graph Database webinar series. I'm Adam Frankel. I'm the host of the webinar series. Today, we'll be talking about an introduction to graph databases with Emil Eifrem. Emil is the CEO of NEO Technology. Previously, he was the CTO of Wind AB, where he led the development of a highly complex information architecture for enterprise content management systems, and he discovered the utility of designing a graph database there. Let me explain some of the procedures for today. On the right-hand part of your screen, there is a control panel including a question box. Please feel free to type your questions in at any time. We will have time at the end of the webinar to answer as many of the questions as we will be able to get to. I already know what the most commonly asked question will be, and that is, are you making a recording of this webinar? The answer is yes, we are making a recording, and after I upload the recording to our servers, which will happen tonight, I will send everyone at this webinar a link to the recording so you can view it later. Let me now turn the podium directly over to Emil so we can get started. Emil, please take it away.
Thank you, Adam. So like Adam said, my name is Emil Eifrem, and I'm the CEO of NEO Technology, which is the commercial sponsor of Neo4j. And Neo4j is an open source graph database and the main character for this webinar today. We're going to do a quick introduction to graph databases. This is adapted from one of the presentations that I give at conferences, and I try to keep my presentations really interactive. It's a bit more challenging with webinars, but we have a couple of interaction tricks up our sleeve. On top of that, I'd also encourage you all to give me feedback over Twitter. The only thing that I do ask of you is that you use the Neo4j hashtag, because we monitor that quite religiously. So the agenda for today is that we're first going to zoom out a little bit and talk about NoSQL for about 5 minutes, and I'm going to walk you through the 4 main categories of NoSQL and talk a little bit about where graph database fit in the broader landscape of NoSQL. Then we're going to dive into graph databases and Neo4j specifically. We're going to look at some use cases, and then it's time to wrap up and Q&A. But before that, Adam, could you run the first poll?
Okay, the first poll is up. Can you see the poll, Emil?
I cannot see the poll.
Okay, so I'll read the options on the poll. The question is, what is your level of graph database familiarity? And the possible options are, I had never heard about graph databases before this webinar, or I have been casually following Neo4j/other graph databases, or I have played around with Neo4j for evaluation purposes, or I have built or am building a real project on Neo4j, or I have put Neo4j into production. And this is a multiple choice poll, so you can select multiple options if they apply to you. Okay, I am going to close this poll and show the results. Let me put the results up. Emil, can you see the results screen?
I can. And it looks like we have about 5% that had never heard about graph databases before this webinar. About half of them, as we see here, have been casually following Neo4j. And then about equal amounts have evaluated Neo4j or are building a real project or have built a real project. We don't have a single person that's put it in production on in the webinar today, which is excellent. And you guys will probably learn something today. Okay, let's get back to the agenda, to the actual webinar slides. So now we're in the brief overview of NoSQL part, and so let me tell you a little bit about NoSQL. Let me see, just make sure that I have presentation back. So one of the things about NoSQL is that it has a horrible name. A lot of people think that NoSQL means never SQL or no to SQL. But the truth is actually different. NoSQL is actually not only SQL, as in the observation that in the backends of the future, we're going to use not only SQL databases, but also key value stores and graph databases. NoSQL has the distinct disadvantage of being in a hyped word. It seems like there's hundreds of new, NoSQL projects getting launched every month. And one of the problems is that sort of the word is defined by what it's not. It's not SQL. It's not defining what it is, however. But if you squint a little bit, you can look at all these new projects and broadly categorize them into 4 categories. The first category is then key value stores. And the key value stores were born out of a research article published by Amazon a couple of years ago. Basically, Amazon said, listen guys, we've built a really high-end e-commerce system. We pushed e-commerce probably to levels beyond which anyone else has been able to take e-commerce. And we did this not by throwing out the relational database, but we actually were forced to build our own specific type of database, specialized type of database. We call this database Dynamo. And the data model of this database is basically a global distributed hash table. So you have a collection of key value pairs. You can think of it as large skinny tables with keys and key columns and value columns. This spawned a number of open source projects. One is called Project Voldemort out of LinkedIn. Another one is called REAC and Tokyo Cabinet. And they all implement the same data model, and it's sort of inspired by this Amazon Dynamo paper. So that's the first category of NoSQL. The second category of NoSQL is the column family or big table clone category. And these were all based on an equivalent paper published by Google, where Google said basically, hey guys, we've also been able to push our systems to some extremes. And we also did this by building our own specialized type of database, and we call it Big Table. And the Big Table data model is creatively that of a big table. So it has a large tabular structure. The unique thing about this data model is that every individual row can have its own schema. So you can have one row which has, let's say we're modeling a salary list, then in one row might have 3 or 4 titles, whereas another row might have 1 title. So you can have a completely unique schema in every single row, at least in theory, in every single row, which is very powerful to capture more messy data models than what the relational database is good at. Examples in here are HBase from the Apache Hadoop project, Hypertable, which is equivalent to HBase but written in C++, and one of the most popular ones is called Cassandra. So that's the second category. The third category is that of document databases. And the document databases were actually inspired originally by Lotus Notes. We don't have an age distribution of the webinar participants, but those of you who have been around for a while might know that Lotus Notes is probably not the best email system in the world, but it actually has a pretty cool back-end architecture, which uses a hierarchical model with a lot of online-offline sync and replication. And that is what the founder of CouchDB looked at. He actually worked at Lotus Notes, and he took that and sort of upgraded it to the 21st century, where he built CouchDB, which has the Lotus Notes, an equivalent, at least conceptually equivalent data model, which basically takes an abstraction of key value pairs that they call documents, and then you can organize these documents sometimes in collections. And so you basically model your world using these key value collection called documents. And the most popular, CouchDB was the first document database to gain popularity, but today by far the most popular one is called MongoDB. I'm sure many of you have heard of that one. And then the fourth category is graph databases, and this is obviously my favorite corner in the NoSQL world. This is sort of tongue-in-cheek, inspired by an old mathematician called Euler who implemented graph theory. And the data model here is very equivalent to the document data model. So in the document database, you had a collection of key value pairs that they call documents. In the graph world, we call these collection of key value pairs nodes. But on top of that, you can also have typed relationships between these nodes that tie them together, as well as key value pairs on the relationships as well. We'll obviously spend a lot more time on graph databases within the next 45 minutes. Examples here are Allegro Graph and Sonas, and of course a product with which I have some familiarity called Neo4j. If we look at these four categories, you can actually see that they have slightly different focus. NoSQL gets a lot of a noise and buzz around scalability, and a lot of people are talking about that. But what not as many people may realize is that there are actually two axes to scalability. One is how do you deal with data set size, i.e. data sets that are growing in volume but are sort of equivalent in nature. The other one is how do you deal with data complexity? How do you deal with data that is increasingly messy, increasingly connected, increasingly semi-structured? And if you look at these four models, we have the key value stores all the way up in the left-hand corner. They're amazing at handle data set size. They have a very simple, some may say simplistic data model. It can typically not express very complex data, or at least makes it very difficult to express that. But the trade-off there is that since the data model is so simple, it is very easy to get it to scale horizontally. And if you want to get to really big data set size, horizontal scalability is your friend. We have the column family or big table guys who have a slightly richer data model. Remember there's a big table where every individual row could have its own schema, so you have more capabilities in terms of handling complexity, but it's slightly more challenge to get the scale to size. You have the document databases, and all the way to the right are the graph databases. The graph databases are amazing at handling complexity. So if you have a domain that is very rich, that is connected, that is semi-structured, then graph databases are awesome. The flip side to that, however, is that if your data is very connected, it becomes really difficult to get it to partition neatly into horizontal buckets so that you can scale out horizontally. So they're more challenging to get to scale to data set size. We'll talk more about that later. Of course, the kicker here, and why I'm most interested in the right hand of these two axes, is that I'd say 90% of the use cases in the world are substantially below where any one of these NoSQL databases get to scale to size. And a graph database like Neo4j, for example, handles hundreds of billions of nodes and relationships, which is more than enough in terms of data set size for the vast majority of the use cases. For some of the big web properties in the world, like Amazon and Facebook, they do need to handle thousands and tens of thousands of machines. And for that, key value stores are also very, very useful. A final thing that I want to mention about NoSQL as a whole before we dive into graph databases is that all of these models are known as, well, are called isomorphic. And isomorphic basically means that you can take data in one of these models and transform it into one of the other ones. But the interesting point is that graph databases are actually a superset of all the other data models. So for example, if you want to, you can take a graph database and trivially simulate the document database by just ignoring the relationships. And the nodes are the exact equivalent to the documents. And the same is true for the document database versus the key value store. If you want to, you can simulate the key value store by just putting everything in a single document. Then you get the equivalent data model from a document database as in the key value store. So the interesting point all of a sudden is not can you store your data in one of these categories. The interesting point is that can you find a data model? Can you find a database data model that lends itself well to your data? If you look at your data set, is it more connected? Then you probably should look at the graph database. Is it very, very tall and skinny tables? Then you should probably look at the key value store. This is us. And this is where we're going to spend the next 45 minutes talking about. So Adam, can you run the second poll, please?
Okay, the second poll is up. Can you see the poll, Emil?
I can see the poll. So the second poll is, why are you interested in graph databases? And this is also a multiple choice question, and we're going to close it in about 10 seconds. So make your make your choice quickly. Why are you interested in graph databases? These are the options you have to choose from. First off, I'm not interested. I clicked the wrong link. Hopefully, we're not going to get too many of those. And the second one is, many domains are graph-oriented, which maps poorly to tables. And the third one is, well, if you have connected data and you put it in SQL, you get quite a lot of performance problems, and that's why I'm interested in graph databases to solve that. And the fourth one is that I realize that graph databases will become increasingly important, for me in my profession, and that's why I'm trying to stay ahead of the curve by learning, getting in early and learning them now. So Adam, please close the poll. And, well, unfortunately, we had 2% saying that I'm not interested. I clicked the wrong link. Well, I apologize for that. Hopefully, you're going to get hooked anyways and get out of this webinar thinking that graph databases are the best thing since, well, sliced bread. And then 60% of you think that many domains are graph-oriented, and that maps poorly to table. This is what I call the compile time advantage of graph databases, i.e. it's an advantage for you as a developer when you sit down to write code. And 54%, so almost equivalent, have what I call the runtime, have runtime problems which are solved with the runtime advantage of graph databases, i.e. performance problems due to joins. And 70% of you think that graph databases will become important to my profession in the future. That's an interesting breakdown. Please flip back to the presentation, Adam. Okay, so now let's zoom in on graph databases, and specifically Neo4j. So we already mentioned this a little bit in the NoSQL overview, but there are 3 core abstractions in the graph database model. If you think back to when you first learned relational databases, there were also 3 core abstractions. There were tables that consisted of rows and columns. In here we have nodes, and the nodes are sort of equivalent to the rows in a relational database. We have typed relationships between these nodes, and they don't have an equivalent in the relational world. You have to model these relationships using join tables, which is one of the problems that we just talked about in the poll. And the third abstraction is key value properties that you attach to both nodes and to relationships. So that's the first pillar. And let me give a quick example. Let's say that you wanted to model a domain, and I chose to model the domain from the Matrix movie. It should come as little surprise to you that I'm a fan of the Matrix movies. That's why the company is called Neo Technology, and the product is called Neo4j in the first place. But let's say that we wanted to model the social network from the Matrix movies. Now, the first thing that you do when you model a domain using a graph database is that you identify the entities in your domain. And those entities will be represented by nodes. So in this case, we have a person, and his name is Thomas Anderson, and he's 29 years old. Well, we have a node to represent that entity, and we have key value properties, name and age, to represent the attributes of that entity. You can see here that we can store values that are strings and that are ints. And any primitive in the Java virtual machine, so bytes, ints, floats, etc., are valid values in Neo4j. But we can also, on top of that, store strings as well as arrays of all of these primitives. So that's the first thing you do. You identify entities. And here we have a couple more entities. We have Morpheus and we have Trinity. And the second thing you do is you figure out how are they related to one another. And in this case, Thomas Anderson knows Morpheus, and Morpheus knows Trinity, and Thomas Anderson knows Trinity. So pretty straightforward. You represent the relationship between entities using relationships. And these relationships have a type, which ends up being really important. It turns out that in many domains, the interesting thing is not just to know that people are connected, but how they are connected. It's wildly different if Thomas Anderson knows Trinity or if he works with Trinity or if he's in love with Trinity. Three very different things. So the types of relationships end up being really important. The second thing that I want to point out here is, as you can see, we've annotated the relationship between Thomas Anderson, node 1, and Trinity, node 2, with a property. And as you'll see later on when we dive into code, we will get to code, I promise. The relationships are first-class citizens. You get the relationships back as objects, and you can work with them on the same level as you work with nodes. You have property container, an interface called property container, which takes key value pairs, and you can add them to the relationships as well as to the nodes. This also ends up being very, very important in many domains. So after we've done that, we just keep identifying more and more entities, and we connect how we figure out how they're connected and use relationships to represent that. And as you can see here, between node 13 and node 42, we actually have a new type of relationship. It's been about a decade. I'm not sure if you have the Matrix movie fresh in your minds. If not, please let this webinar serve you as a subtle reminder for you to go to watch that movie again, because it is amazing. But if you do not remember the mythology of the Matrix movies, basically the bad guys in there were software programs. And you can see here node number 13, Agent Smith, is one of the bad guys, and the most evil thing I could come up with is that he's coded in C++, as you can see there. So here you can see a small social graph. We use two relationship types. We use nodes, and we use key value properties to express the domain. If you look at the code from this, it is fairly straightforward. Most people pick up the representation part of the code really, really quickly, how you represent your domain in a graph database. So first off, we get a graph database service, and just before we get any further, I want to emphasize the fact that I've used Java here because Java is widely read by most professional developers today, but there are bindings to Neo4j for pretty much any language on the planet. There's Ruby bindings, there's Scala bindings, Clojure bindings, there's C# bindings, PHP bindings, etc. I've used Java for illustrative purposes here. So we get the graph database service somehow from probably from our dependency injection container, and then we use that to create the node. We get a node back, and we use set property, get property. This is from the property container interface that also relationship implement. And it's very semantically equivalent to a hash table. And then you can see the last line. We take the first node, Mr. Anderson. We invoke a factory method on that called createRelationship2, and we pass in the second node, Morpheus. And we also pass in a type, in this case indicating that Mr. Anderson knows Morpheus. An interesting thing to note about working with Neo4j, which sets us apart from many of our brothers and sisters in the NoSQL space, is this. You have to wrap any mutating operation in Neo4j in a transaction. We think that transactions are fundamentally really, really important to build enterprise-class applications. We think that there's a lot of room for eventual consistency, and the base view of consistency semantics, and in particular when you get to really big scalability, when you get to tens, 20, 50, hundreds of machines, you definitely need to seriously consider relaxing your consistency requirements and get to an eventually consistent model. Having said that, though, we think that an eventually consistent system should be built on a core of ACID, real strong consistency semantics, which is what we have. That's one of the things that sets us apart. And our transactions work the same way that transactions work in a relational database. Basically, all of these operations will be committed at once or none of them. And when you commit, it is guaranteed durable on disk. You will never, ever lose data. Once commit has returned out, it is guaranteed to be on disk. So they work basically the same you would expect if you have a relational database background or experience. So we talked about relationship types, and there's actually, if you recall from the previous slide, we passed in rel types.knows in the last line to describe the type of the relationship between Mr. Anderson and Morpheus. And in our API, there's actually a simple interface called relationship type, and it basically says that anything that has a name method is a relationship type. There's no need to go in and use an equivalent of a create table or anything like this, but you can just implement this little interface, and then the first time that the Neo4j kernel sees a new type of relationship, it's going to automatically create that underlying in the graph database, and there's no need to do restart or anything like that. It will just work completely dynamically. So you can see here, one example is that you could implement a completely dynamic relationship type, super simple, 3 lines. You have a string name, you pass that into the constructor, and you return it, and that's it. You can imagine, for example, if you would you would spider the web, you could detect a new condition, and you could dynamically create a new type of relationship. A number of really cool applications have been built and can be built with a completely dynamic relationship model. Having said that, though, in many domains, you actually do know beforehand. When you sit down and you spec it out on your whiteboard, you actually know that, well, we have bank customers, and they have a bank account, and the bank account is connected to an account balance, etc. So ahead of time, you actually know. And if you're in that model, you can actually use an enum in Java to declare your relationship types. And they will then be completely static, which means that your IDE will do code completion with them. Your compiler will complain. You will be unable to create a new relationship type if it doesn't already exist, declared in the enum, and all the other benefits of static typing. So these are the 2 ways you can work with relationship: completely dynamic, completely static, or actually a hybrid if you so choose. I want to take a quick step back and talk a little bit about one observation that we made that we called whiteboard friendliness. And whiteboard friendliness is a very powerful concept, and it stems from way back in the days when we first had built the initial version of Neo4j, and we worked as consultants. One of the first things that we did when you get into a new project is that you get domain experts and business stakeholders into a room, and that room is typically wallpapered with whiteboards, and you brainstorm and you talk about the domain. And these people are folks that are experts in pensions, or experts in retail, or experts in a domain, but they don't know anything about databases. They don't know anything about third normal form. They don't know entity relationship modeling. They don't know any of those things. They have not been through a CS education typically. And the observation we made was that, hey, very seldomly do you in this situation end up drawing tables on the whiteboard. More often than not, it's a much more messy picture of entities connected to other entities, and sometimes with a type, and then you end up drawing something that actually more often than not resembles a graph. At least it's a big, messy picture. And the astounding thing that we observed was that when we built that system and put it in production 6 months later, we could look at the pictures, the snapshots we took, the digital snapshots we took from the initial brainstorming sessions, and we could see a one-to-one mapping between them and the graph. And I think that's a super powerful concept, because I think the cognitive model of the programmer is that of the domain as it is drawn on a whiteboard. That is the cognitive model. We may have been trained to use ER modeling and whatnot to get from that conceptual model to a partition, a serialization into tables. But that is not the intuitive model. And the fact that you can see that and have a one-to-one mapping in the data, in the graph that you look at, I think that is one of the reasons why it feels so powerful and fast and effective to be working with graph databases. We call this whiteboard friendliness. All right, so we now learned how to put data into the graph database. And the second thing we want to learn is how to get data out of it. And by the way, there you have a question box, I believe in your right-hand corner. Please file questions in there. I'm not going to be able to attend to them right away during the presentation, but we will have a Q&A session at the end, and we will make sure to follow up with all the questions eventually. But please keep them coming continuously. Okay, so we know how to put data in there, but of course there's no use putting data in there if you can't get it out of there, right? And for that, we have a traversal framework. If we take then a step back to our example, the Matrix example, the social graph from the Matrix movies, what if we wanted to figure out the friends of Mr. Anderson? So let's assume that we want to know both his direct friends and friends of friends of friends, sort of infinitely until we have this entire friend graph. Conceptually, what we want to do here is we want to start at the first node, the Thomas Anderson node, and then we want to traverse breadth first rather than depth first. Breadth first because we want his closest friends first. Along the relationships of the nodes types. We want to start at 1 and then go to 7, 2, and then 3, and then 13. And then we want to stop at 13, right? Because there are no nodes relationship types going out of 13. There's a relationship of the type coded by, but that's not what we're looking for. We're looking for friends here. So that's conceptually what we want to do. Pretty straightforward. The code for that, and this is the peak of the complexity of this webinar, so if there's any time you should grab that cup of coffee right next to you and down it and then focus, this is it. So this is how you declare a traverser. The first thing is that the traverser is a Java iterable, which is basically an iterator, so a way of incrementally walking a data structure, in this case the graph. We get that out of a factory method on the node. In this case, Mr. Anderson.traverse. The factory method is called traverse. And what we do, the magic, if you will, is in the parameters that we pass into traverse, because that is what's going to instruct the traverser framework how to crawl the graph, how to walk the graph, and what nodes to return back into the traverser. So the first one we pass in is breadth first, because I mentioned that we want to go breadth first, and breadth first is like a wave. If you throw a rock into an ocean, the waves will go breadth first. We want to go that because we want his closest friends before his not-so-close friends. And then we want to instruct the traverser framework to only walk along the relationship types called nodes, relationships of the type nodes, in the outgoing direction. And after that, we pass in 2 so-called evaluators. And the first evaluator is called a stop evaluator. And this stop evaluator will instruct a traverser framework, basically a termination condition, when to stop walking the graph. In this case, we say end of graph. Traverse as long as you can find relationships that match the filter below. And the filter, again, is nodes relationships in the outgoing direction. And then the second evaluator is a returnable evaluator, which says that out of all the nodes that we're going to visit, what nodes should I include in the result set? In this case, we say all but start node, because we want every node that we visit except for the first one, because again we wanted Mr. Anderson's friends, not Mr. Anderson himself. All right, so after we declared that friends traverser, nothing at all has happened. The only thing that has happened is that we've positioned that traverser on Mr. Anderson, because that's because we executed the traverse method from the Mr. Anderson node. That's the only thing that has happened. We're not going to do any type of queries or traversing or walking the graph until we incrementally start invoking next on the friends traverser. And this turns out to be very, very useful, particularly in web applications, where sometimes even though you get hundreds of thousands of hits, you may only be interested in the 10 first or the 11 to 20 when you do paging. And that's what an iterable idiom gives you. I think the second code is fairly intuitive if you know Java 5 syntax. Basically, for every friend, which is a node, in the friends traverser, we're going to print out a couple of interesting things. One is we're going to print out the property name on that node. And the second thing is we use the friends traversers to access the current context of the traversal. And specifically, we want to get the exact current position of where we are and the depth that is. So we're going to print out, if you're a depth 1 friend, you're very close. If you're a depth 2 friend, you're, not so close. And depth 4, of course, you're far away from me in friendship. So let's dive into one example of this. So the first thing that's going to happen here, and I'm going to walk you through the first 2 steps in detail, and then it's going to be very obvious. So we start at node number 1, and the first thing that the traversal framework does is that it's going to invoke the returnable evaluator on this. And it's going to check, all right, I'm now on one node, returnable evaluator, should I return this node? And in this case, we have a returnable evaluator called old but start node. And this is the start node, so we're going to say, no, we're not going to return this node. All right, then the traversal framework will invoke the stop evaluator. And it's going to ask, all right, is it time to stop my traversal? In this case, the stop evaluator says, no, never stop. Just keep traversing as long as you can find relationships that match your filter, keep traversing. We want all of Mr. Anderson's friends. So then the third thing that the traversal framework does is that it's going to look at all the relationships on this one node. And it's going to pick one that matches the filter, knows in the outgoing relationship, in the outgoing direction. In this case, we have 2 relationships. It's going to grab one of them, actually at random. Let's assume that it's the first one between 1 and 7. It's going to walk that relationship. It's going to end up at 7. It's going to look at the returnable evaluator, which then is going to say, well, we're not at the start node now, so yeah, let's return this. And number 7 will be returned out of the traversal. When we invoke next again on the traverser, what it's going to do is it's actually going to go back to 1, because remember, this is breadth first rather than depth first. So it's going to take a step back to 1 and then take the second relationship that matched the filter. In this case, that was nose in the outgoing direction. Why does it do this? Well, because it asked the stop evaluator, which told it to just keep traversing as long as you can. So that means that it's going to go back to 1. It's going to go to the across the other relationship and end up at 2. 2. It's going to ask the returnable evaluator, well, is this one okay? Should I return it? And it's going to say, well, this is not the start node, so let's return that one. And after a while, you can see that we're printing Morpheus, Trinity, Cypher, and then finally we're printing Agent Smith. And the kicker here, of course, is that if you know the Matrix movies, Agent Smith was the mortal enemy of Thomas Anderson, Neo, right? But it turns out that they had a traitor in between them. Cypher was the guy who knows both the freedom fighters as well as the bad guys. And if they had only had a graph database, they would have detected this way earlier, and the movie would have been way shorter. So that's all fine and dandy, but what if we want to do some more sophisticated queries? Let's say that we modify our domain. Let's say that we want to add love semantics to our social graph. So we want to express that Trinity here is in love with Thomas Anderson. And what if we want to do another type of query that says, well, look at the same type of subgraph that we looked at last time, i.e. the friends of Mr. Anderson, but only return friends that are in love, right? Turns out that conceptually what we want to do is very similar. We want to start at node number 1. We want to traverse all the relationship in the nose of the nose type in the outgoing direction. And we want to keep traversing, but we only want to return the ones that have a loves relationship type attached to them in the outgoing direction. So the code for this is pretty similar. We now declare a new traverser, the love traverser. We pass in breadth first. We say stop only when you get to the end of the graph, because we again want to, we want to have all of Mr. Anderson's transitive nodes. Transitive friends. We say that traverse along the nose relationships in the outgoing direction. But the interesting thing is, what should our returnable evaluator be? If you recall, in the previous example, the returnable evaluator was all but start node to return everyone except for Mr. Anderson himself. In this case, we actually want something slightly more complex. And here you can see that these evaluators are actually interfaces that you can pass in anonymous or known implementations of. And here is sort of where Java as a language probably does not shine as much as some of the newer languages, because if you set aside some of the syntactic cruft in here, This is really just a one-liner. We're passing in one line, which starts with position, pos.current node. It checks if it has a relationship of the loves type in the outgoing direction. If it does, that whole line there, that whole statement will return true. We're going to return true out of the isReturnableNode method, which means that we will include the node that we're visiting right now in the result set. So pretty straightforward, right? And then the printout loop is roughly identical to the one we used last time. So in this case, we're going to start at 1, and we're not going to return 1 because 1 does not have a return about the return evaluator will not return true in this instance. Because why not? Well, number 1 actually has a relationship of the loves type, but it's not in the outgoing direction. It's in the incoming direction. So as it goes on and keeps traversing and visits 7, the returnable evaluator will return false because there are no relationship of the loves type. But as it visits number 2, it will be true, and number 2 will be returned out of the evaluator. I'm sorry, out of the traverser. So the example here is pretty straightforward. It's going to be Trinity. So that is it for the core representation and traversal API. What I've taught you right now is the equivalent of SQL select and insert statements. This is a low-level API on how you interact with the database. But what if you want to implement your own domain model, which I'm going to assume that many of you want to do. Well, it turns out that what you want to do with a graph database like Neo4j is you want to use the delegator pattern for that. The common way to do this for a relational database is that you would implement your domain layer, and then you would have a separate mechanism, the OR mapping framework, that would look at your domain objects, or POJOs in Java, plain old Java objects. You would look at them, and the OR framework would take that and it would translate that into tables and write it down to the relational database. It turns out that for various reasons you don't have to do that with a graph database. With a graph database, instead you use the delegator pattern. So let's assume here that we have a person interface. That person interface includes a getName and a setName method. We have an implementation of that we call person_impl, and here's what it might look like. That person_impl will have only one actual attribute, and that attribute is going to be a reference to the underlying node that represents this specific person. If you implemented this in a relational model or using JPA in Java, then typically what you would have here is a private string name, and then your getName and your setName would work with that private attribute. But here instead we store a reference to the graph. We get that reference at instantiation time, where you pass in that node. And getName actually, rather than looking at the local attribute, delegates that to the underlying node, which gets it from the graph database, right? So you get the property called name, you cast it to a string, and setName is equivalent. Basically, you use the set property instead. You take the passed-in name and you set that on the node. This has a number of advantages because all of a sudden you don't have any state at all in your domain layer. All state is kept in the graph database. And one of the things that databases are good at is handling transactionality. That handling state is really all a database does. So all of a sudden now you have a situation where since all your state is kept in the database, even in your domain layer, your domain layer state is kept in your database. You can execute rollbacks and do proper transactional semantics against your business layer. This means that you don't have to use any kind of synchronization primitives in your domain layer. You will just delegate all that to the graph. And so, for example, if you have multiple people reading and writing to the same person, then you're going to get the same kind of semantics as you would expect out of the database, i.e. all these different concurrent threads will all read a consistent view until one of the threads have written something, and when it's published, that gets published to all the concurrently reading threads. So real transactional semantics. And this is called software transactional memory, STM, and is one of the approaches that we as an industry have to deal with the multi-core, highly parallel systems that we need to to write these days. It turns out, though, that after a while it becomes tedious to type up all of this code. It's sort of repetitive. And so a number of people and projects and frameworks have tackled this. One is called Qi4j, QI4j, and it's a framework for doing domain-driven design in pure Java 5. And Neo4j is an entity store backend to that. Another part is called Jo for Neo, which basically uses annotations to declare your POJOs, your plain domain objects. You annotate them, and that's going to be used to drive persistence into Neo4j. And the third one, and one that we're spending a lot of time on these days, is called Spring Data Graph. And it is part of the umbrella Spring Data project that we are working a lot with in tight partnership with SpringSource around. It basically provides a similar in spirit model to Jo for Neo, but in a much richer way. So basically you can go in, and in the previous example, if you have a person, you would still declare a private string name, but no state will actually be stored in that. You would actually intercept that using aspects and write it down into the graph. So if you go from your normal domain object, you just add one single annotation. You annotate it with node entity. Before you had a person, if you wanted to store it in a relational database, you would annotate it with @entity. And if you want to store it in a graph database, you annotate it with @node entity. And that's it. You're done. An incredibly powerful way of working on a domain layer, but still get access to the full power of a graph database. Okay, that's all fine and dandy, but what are some use cases for this? If we're really briefly going to look at some of the things that people are building with graph databases, the first and most obvious one is social data, right? We used an example previously from the Matrix movies, and really any type of data that is social lends itself really well to a graph database because it so fundamentally is centered around how people are connecting to other people and other places and other objects. So that's an obvious, really huge use case for graph databases. But the interesting point about this, a lot of people think that graph databases are just about social. But of course, the graph database doesn't care what gets stored in the graph, right? I mean, these are just properties and relationship types. It could be anything. So if you keep the exact same structure and just add other types of relationships, other types on the relationships and other properties, all of a sudden we can store spatial data. So in here, the nodes represent not people, as in the previous example, but actually points of interest. So there's apparently a place called the Omni Hotel, which is represented by node number 1. There's a road between place 1 and place 2, and the length of that road is 3 miles. We use the length or the distance. We annotate with property on the relationship. And you can see that it's really simple to figure out how to get from point A to point B using basically shortest path graphing algorithms. It lends itself really well to graph databases. But we actually support even richer spatial queries than that. As you can see in this example, we've annotated the nodes with 2 properties called lat and long, latitude and longitude. And if you do that and you use our Neo4j spatial support, you can actually answer real radius queries like, give me all the nodes within 30 miles from this node. Or give me all the nodes that intersect with this one bounding box, etc. True spatial queries. Very, very powerful. But we now talked about both social and spatial. Well, you can actually combine social and spatial. And if you do that, you get to basically these location-based services like Foursquare or Gowalla or Facebook Places, where if you can see on the right-hand side of the screen, you have a social graph. You have a guy called Emil, and he knows a guy called Peter, and he has a sibling called Maria. And on the left-hand side, we have nodes still representing these points of interest from the geography space, right? But we've tied them together. And all of a sudden, we can answer really sophisticated queries. For example, give me all the taverns or all the places within 30 miles from where I am right now where they serve beer, and that please rank them according to the recommendations by my friends. And in fact, my friends, I trust my friends differently when it comes to beer qualification. In this example, just hypothetically speaking, the node number 3, which has a name Emil, have a beer qualification as expert, whereas his sibling Maria has beer qualification as non-existent. She apparently doesn't know anything about beers. So in that situation, you probably want to weight Emil's recommendations way higher than Maria's, right? Because Emil is more of an expert. And that type of query, give me all the places within 30 miles that are recommended by my friends, ranked by that recommendation, but also weighted by their qualification, is a trivial query to do in a graph database. And here we can start to see the power of having the flexible model that the graph databases uniquely possess in the NoSQL space, because you can add these multi-layered graphs all together and combine them in the same database instance, in the same database model, to yield really powerful query results. Another example is from the finance industry. So you can imagine that you have a bunch of transactions going on at really high speed, and these transactions are of the form that money is now being exchanged from entity A to entity B, and entity A may be a person, and entity B might be a store or something like that. And what many folks in the finance industry are interested in figuring out at really high performance is fraud. Is there a potential for fraud in here? And in this example, we've taken those transactions and we've built up a graph. So we have node number 13 on the right-hand side of the corner of the screen, which represents an ATM. And Emil has withdrawn, node number 3 has withdrawn cash from the ATM, has transferred it to this one beer tavern. And it turns out that that tavern is owned by a bad guy, Mr. Godfather in this example. And what we want to do in order to figure out fraud is to check what is the path between the ATM and this potential suspect, node number 1. And that is the shortest path algorithm in a graph database. And for many of our big finance customers, they need to do thousands of these kinds of transactions per second and answer queries at sub-millisecond time. A very good use case for graph databases. Very complex data, very high query real-time performance requirements. Okay, a couple of notes on the system characteristics of Neo4j. It's completely disk-based. We've written our own native graph storage engine, which is completely oriented to be lightning fast at traversals. We're going to get into an example pretty rapidly. It's fully transactional. We mentioned this already, but I want to really drive this point home. We're completely XA compliant, which means that we can participate in transactions between Neo4j and an Oracle database, for example, which is an important point if you run enterprise class systems. We do deadlock detection, multi-version concurrency control, all that good stuff. And the most important point is that we never, ever lose data. We've been singularly focused on robustness, and we've been up and running, which is one of the next points here. We've been up and running in 24/7 production for 8 years now. So Neo4j has an incredibly solid and robust core. Scales up, handles billions of nodes, I think hundreds of billions of nodes and relationships and properties on a single JVM today, and we're consistently working to increase that upper ceiling. So scales up really quite well, and we're going to talk a little bit, or at least mention that it also scales out using master-slave replication in Neo4j HA, high availability. Let's spend a little bit more time on performance. A while back, we were contacted by one of the biggest social networks in the world, and they said basically, look, we've been looking at NoSQL, and we see that graph databases by far are the most powerful model. This is really the way you want to work with data today. However, we're a big social network X, and the only thing we really care about is performance. So, how fast are you, and can you show us some benchmarks? And us being the honest geeks that we are, we said basically, look, we can prove anything with benchmarks. So how about you give us a scenario, and we'll show you how fast we perform in that specific scenario. Make sure that it's relevant for you. And so they did. So we got a scenario which was as follows. Assume that we have a social graph of 1,000 people. We have 50 average friends per person. And we grab 2 people at random. And then we check, is there a path between these 2 people? And we limit it to depth 4 because otherwise everyone is going to be connected to everyone. We implement this using 2 backends, an unknown but, well, unmentioned but widely popular open source relational database, and Neo4j. But we eliminated disk I/O because we wanted the overhead of the actual model, not of going to disk. So we warmed up the caches. And in this example, the relational database, again, remember, we're grabbing two people at random, for example, Mike in this example and Kevin. And then we check, are Mike and Kevin connected within 4 hops? So Mike to Emil, Emil to Marcus, Marcus to John, John to Kevin. 1, 2, 3, 4. The answer would be yes, between Mike and Kevin. In the relational database with 1,000 people and 50 average connections, so 25 million relationships, 25,000 relationships, we have a query time of 2,000 milliseconds for that query. This is what's called an arbitrary path length query in SQL. The SQL code for this ended up being 4 pages long. It is huge because you need to check, is Mike connected to Kevin on level 1 or on level 2 or on level 3, and the same for Kevin and the same in both directions. It's a very large and complex SQL query to write. But that's not the worst part of it. The worst part, of course, is that it ends up doing, I think, a 32-way join. And this is what I like to call the sweet spot of suck for SQL, arbitrary path length queries. One of the really high performance problems in relational databases. In Neo4j, that same query is 2 milliseconds. So it's 1,000 times faster. Grab 2 people at random, check if they're connected, 2 milliseconds, bam. But we weren't happy enough with that, so we upped the ante a little bit. We added 1 million people to that, and it's running on my previous laptop, so a 300 megabyte laptop. A laptop with a 300 megabyte heap assigned to the JVM. And we still have 50 average friends, so there's a total of 25 million friends relationships in this graph. We grab 2 people at random and check if they're connected within depth 4. And with Neo4j, for that, it's still a 2 millisecond operation. So it's substantially faster than a relational database. And I usually get the question, how long time did that take in the relational database? And honestly, we aborted after several days. So when it comes to high performance traversal of complex data, a graph database is typically a very good fit. So pros and cons compared to a relational database. Well, there's no OR impedance mismatch. It's much easier to store many domain models in a graph database. It's easy to evolve schemas because it's a schema-free model. And it can represent semi-structured info. If you recall, you can attach 5 properties to one node and 3 properties to another and 10,000 properties on a 4th node. And there's no single schema pushing down, forcing all elements to look the same. And finally, as we just saw, we can represent graphs and networks with really high performance. But there's definitely cons as well. And one of the big problems right now, if you want to work with graph databases compared to relational databases, is lack in tool and framework support. And this is an obvious one. While we have been working on this for 10 years inside of Neo Technology, the industry has worked 40 years on relational databases. And relational databases integrate with Excel, they integrate with, there's a bunch of OR mapping frameworks, reporting tools, etc. Some of that is quickly getting built for NoSQL in general and for graph databases specifically. But there's still not the breadth of tools and frameworks available for us as with a relational database. The second one is that currently there are few other graph database implementations, and that's a bad thing. I mean, for you as an end customer, you want many graph database implementations. There are certainly a lot more today than there were just 2 years ago. So there are viable alternatives out there. But I have to say, though, that, and I think I'm being completely objective about this, if you take a graph database and really push it to its extremes, Neo4j today is the only choice. And that is a bad thing, and hopefully something that's going to change in the future as other databases become, as other graph databases become more and more mature. And the third classic problem with a graph database versus a relational database is no support for ad hoc queries. But actually, that has changed as of a very recent release of Neo4j, where we launched the so-called Cypher query language. And if you recall from the traversals that we did before, all of them were programmatic. And that's actually really useful if you're writing an application you want to work with a Java programming language or with Ruby or something like this. But in many cases, you just want to go in and you want to query the database using a declarative syntax for ops reasons, for DBAs, and sometimes even in your application. And for that, we have Cypher. So one example of Cypher, let's say that we wanted to find all the friends of friends of a guy called John in here. We have 3 core components of this Cypher query. The first component is the starting point. Where in the graph should I start? And here we say, grab a node called user, and that node should be looked up in the people index by the name of John. So grab John, the node representing John. And then we match. And the match statement here, I hope you can see it really draws an ASCII visual representation of a small subgraph. So we say user, and then it has a relationship of the friend of type to a node that could be anything, any node, which then has another relationship to a node that we call FOF, friend of friend, and then return that friend of friend. So what Cypher is going to do here, it's going to start at the John user, and then it's going to grab that John user, it's going to traverse the friend of friend relationships, all of them, and then their friend of friend relationships, and get to the target node there and return all of them. You can actually qualify, so you can declare multiple starting points. In this case, user will first be node 1, and then node 2, and then node 3. And we can qualify the return nodes by saying, for example, in this case, only return those followers that have an age that is greater than 18. And in fact, don't return the follower, but return the names of them. So in this case, it would take all the 3 nodes with ID 1, 2, and 3, and give all their followers that have an age more than 18 in their names. So that's Cypher. We're very excited about that, and it's part of the 1.4 release that we released just a couple of days ago. We also support Gremlin, which is a very popular and very powerful groovy DSL for expressing graph traversals. So it's on a higher abstraction level than our traversal framework, and you can actually serialize it across the wire. This is part of the Tinkerpop graph stack, which has a bunch of good, rich features that builds on top of any graph database that I urge you to check out. Google the Tinkerpop for that. There's a lot of information around how to work with graph data using Gremlin. In this case, this simple Gremlin expression here basically returns all my direct friends that have an age more than 18 and their name specifically. I mentioned before that there's a bunch of language bindings. There's Python, there's Ruby, there's Clojure, there's Scala, there's Erlang, etc. For more information about that, there's a wiki page, wiki.neo4j.org, that contains links to all the different programming languages, and as well as other frameworks like Grails and Ru and Rails. And there's a lot more to talk about. We're running we're probably running long by about 5 minutes here, so we're not going to get into any of this, but we have a clustering mode as well, which basically allows you to scale out horizontally and replicate the graph across multiple machines. We have a Neo4j server with a RESTful API that you can use rather than the low-level programming API. And it should be important to note that we have a web admin, which is very useful as a programmer to get up and running, where you can type interactive Gremlin queries. It actually has a visual interface as well for illustrating the graph, and it's completely built into the web admin. We just released Neo4j 2 days ago, and the main features are listed here. You can Google Neo4j 1.4 and you're going to get to the blog post. Cypher, we already talked about. Self-relationships creates loops within nodes. You can create a relationship from one node to itself. And we ship with a number of default extensions, including a Gremlin plugin, which we previously looked at a simple Gremlin query. And by that, I want to wrap up. And I want to wrap up by saying that I hope that you've enjoyed the webinar. I hope that you see that as I summarized in the first item, graphs are awesome and Neo4j is awesome. And it's available to download right now. We have an open source edition. Actually, all 3 of our editions are open source. We have a GPL open source edition called Neo4j Community, which contains everything you've seen today and much more. And then we have commercially supported AGPL editions that add monitoring, management, and that adds high availability clustering, Neo4j Advanced and Neo4j Enterprise. I urge you to go to neo4j.org to check it out. There's also, I want to make sure to mention the Spring Data Graph project. You can see the URL here, springsource.org/springdata/neo4j. And that's a good way of checking out the really powerful support for integrating graph databases in Spring-powered domain models. And by that, I want to thank you all for attending this webinar. We're going to run these webinars on a bi-weekly schedule, so twice per month. It's been a pleasure to interact with you in this first graph webinar series. Thanks. Over to you, Adam.
Okay, thank you very much, Emil, for a great presentation. As I'm sure everyone knows, we are short on time here. We have a lot of questions, and we're obviously not going to be able to get to all of the questions today, but I would like to pose a couple of these to Emil right now and tell you that all of these other questions, if you go to the neo4j.org website, we have an active discussion group. And if you put your question up on the discussion group, you will, each one of these will probably provoke a creative thread, and you will find the answers there. But I do want to answer a couple questions on this webinar right now. And several people there have asked questions about love. And so I figured that I'll make that the theme of the Q&A. Right? So first of all, right, in the example of from the matrix, right, can there be multiple relationships between nodes? In other words, can Neo both know and love Trinity? Emil, do you want to answer that?
Sure. Yes, you can create multiple relationships between nodes. Those relationships can all have the same type or have other types. So the answer is yes.
Okay. Here's a second question in a similar theme. What if Trinity was in love with Morpheus? Will Trinity's node be returned because she only has the outgoing loves relationship? There was no check if the node the relationship points to is the start node.
Yeah. In this question, the traversal example that we used was basically give me all the nodes that are in love, not specifically if they're in love with me. If you wanted to have that, we would add that to the returnable evaluator to basically check that the target, if you will, the end node of the outgoing relationship of the loves type was me. If that is me, then return it. If not, no. So in this case, if she was in love with Morpheus, we would return it because that's the query that we designed.
Okay. And then the last question that we'll get to today is this webinar being recorded? Which, true to my prediction, is the most commonly asked question in this webinar. And the answer is yes. We've made a recording of the entire webinar. I will upload it tonight, probably to YouTube, and I will send out a link to everyone as soon as we make sure that the webinar is properly up there. If we didn't get to your question today, I'm sorry, but we're out of time. Please go to neo4j.org. Right? We have an active discussion group. Any one of these questions would be a great post on the discussion group. Also at neo4j.org, we have registration for our next webinar, which will be about getting started with Neo4j. Please feel free to sign up for that. but most importantly, at neo4j.org, you have access to a free download of the community edition of Neo4j. So please go ahead, download it for free, and try it out. The best way to learn it is to try using it. I want to thank Emil for putting together this great presentation. I'd like to thank our audience. Your time is very precious, and we appreciate the fact that you've given us more than an hour of your attention today. Thank you very much, Emil. Thank you very much, everyone, for coming, and goodbye.
Thank you, Adam. Thanks and goodbye.